These are solutions for assignment 317. Some true-false. A linear approximation will be an overestimate whenever the tangent line is above the function line. So we're using this point on the tangent as an estimate for this actual point on the function. So that would be true for any concave down function. The derivative of 7 to the x. This is our derivative of a to the x, so it should be 7 to the x natural log of 7. So this is a power rule used incorrectly, so this would be false. 7 to the pi is a constant, so the derivative of 7 to the pi would be 0, so this would be false. The derivative of inverse cosine, no, this is actually the derivative of arctangent of x, so that's also false. All right, in question 5, we'll need to do implicit differentiation. So this is just reminding you, this statement here that y represents the function is just to remind you that y really represents a glob of x's. So that's a reminder why we do a chain rule whenever we're using implicit differentiation. So we have to do product rule on this first term. So I'll keep x alone, the derivative of this y term with a chain rule on the y, and then the y term with the derivative of 1x is just 1. And then we need another product rule on xy, so that would be the first term x times the derivative of y plus y times the derivative of x would just be 1. And on the right hand side we'll have a derivative of 6 is 0. And now we can solve this for y prime if you wish, or you could do your substitutions right away. It depends what you want to do here. If I rewrite these two terms that have y prime, I'm going to keep on this side. And these two terms that do not, I'm going to move to the other side. So y prime would look like this if we solved it. X squared y squared plus x. And now we want to do our substitutions. So we are told that the derivative, or we are looking for the derivative at 3. Here we know the ordered pair when x is 3, y is 1. So we want to substitute to find y prime such that x is 3, y is 1. So we would get what? The opposite of 1 minus 1 divided by, putting 3 in for x, we'll have 3 times 9 times 1, so 27 plus 3, so negative 2 over 30, or negative 1/15, and it looks like I have an error, so let me go back and look to see what's going wrong here. All right, I think my error here is just in writing this term, so 3x to the first power. So I want to get rid of that exponent on the x. So let's try the substitution again. When we put 3 in for x, we'll have a 9 plus a 3. So I think we'll have a negative 2 over 12. Or a negative 1/6. So that looks like it fixes the mistake. All right. The derivative, find the value of f prime of 8. So first let's find the general rule for f prime. The derivative of arcsine is 1 over the square root of 1 minus the glob squared. So this time our variable is in the denominator. And then, so this is, in other words, 4x to the negative 1. So then our chain rule is on 4x to the negative 1. So that would be negative 4x to the negative 2. So let's clean this up here. So again, we don't like these complex fraction, so let's write this as x squared over x squared. So x squared minus 16 over x squared, so then we can bring an x out, and we can rewrite this over x squared. So notice that that's over 1, and when we bring this out, this is going to be a 1 over. Absolute value of x is not going to be too important here because we know we're just going to plug in an 8. So you might say, do I have to do all of this algebra to clean this up if I'm just going to do a substitution? And I think that would be a good point. I could have just stopped right here and done the substitution of x equals 8 at this point. So to use your test time wisely on multiple choice, why should we clean up a multiple choice problem? So, but this x would cancel with this one. So if you did the cleanup here, I think this is our formula. And now let's try putting an 8 in there. So we would come up with a -4. 8, 64 minus 16 is 48. So let's do some canceling here. Let's make this a 1/2. And then we'll do 16 times 3. So this is going to bring a 4 to the outside. So I think we've got 8 and then a 3 left. So the square root of 48 I've split up into 16 times 3. So letter A would be my choice. And again, let me remind you that I probably didn't use my time wisely there. Why clean up the problem if you just want to substitute 8? You could have put 8 in right away and then cleaned it up. All right, in number 7, the derivative of a log function is 1 over x, natural log of the base, and then a chain rule on the glob, but the chain rule here would just be a 1, so there's a reason we don't have to do that. And now we want to substitute 1 into our function. So when x is equal to 1, I think we come up with 1 over ln of 2. In number 8, here we've got x in the base and x in the exponent. So let's think of this as y equals. And then we want to do logarithmic differentiation because that will bring the exponent. So we take the log of both sides because then the exponent can come down in front. The log of a power is the power times the log. And now we do implicit differentiation, and on this side we've got a product rule. So I'm going to keep the 2x, do the derivative of the second part, 1 over x, and then I'm going to keep the second part and do the derivative of the 2x. So here we can cancel this x with this x, and then we're going to bring this y to the other side. So I'm going to put y in there. And what was over here is now 2 plus 2 ln of x. And y prime is x, I'm sorry, not y prime, y. When we bring over y, this is x to the 2x. And now we're ready to substitute. So we want to do y prime of 1. So we would have 1 to the second power is 1. Let me get a little space here. 1 to the second power is 1. And here we would have 2 plus 2 natural log of 1. So e to what power produces 1? This is 0. So we would have just 1 times 2 for our result. So I like A. In number 9, we again have x in the base and x in the exponent. Some of these we've practiced before. I hope you'll keep doing them until they are simpler. So we're going to make this a y equals and do the natural log of both sides again. And immediately you can bring the exponent down in front. All right, so we do implicit differentiation yet again and treat this as a product rule. So the first part times the derivative of the natural log is 1 over the glob with a chain rule on the glob. Derivative of sine is cosine x. So this is our chain rule, plus the second function times the derivative of the first. The derivative of x is just 1. So if we clean this up again, and we're going to bring the y to the other side, so I'll just leave a spot here to remind you that we're going to multiply y there, but I can clean this up as x cotangent x if you wish, and the natural log of sine of x, and our y is our original sine of x raised to the x power. And now we're going to evaluate this at pi over 2. So we want to put pi over 2 in. The sine of pi over 2 is 1. So y prime at pi over 2. The sine of pi over 2 is 1. To any power would still be 1. So 1 to the pi over 2 power is still 1. And here we have 1. The cotangent of, oops, I'm putting in 1 instead of pi over 2 for x. Pi over 2 for this x. And now the cotangent of pi over 2. Cotangent is cosine over sine. And at pi over 2, the cotangent is 0. And then the natural log of the sine of pi over 2. The sine of pi over 2 is 1. We did this a minute ago. The natural log of 1 is 0. So what do we have here? It looks like we have 1 times a 0. So I think, if I haven't made any errors, that I would choose 0. And yet one more logarithmic differentiation. We have x in the base and in the exponent. So let's think of this, rewrite this as x to the 1/2 to the x. So power of a power you would multiply. So we could call this x to the x over 2 power. So the natural log, and I want to save some space here, bring my exponent down in front. So the x over 2 that was up here, I've already brought down. And logarithmic differentiation. And here this is 1/2 times x as our first function. So we keep our first function times the derivative of the natural log of x plus the natural log of x times the derivative of 1/2 x. That would be 1/2. These x's cancel. So we now are going to multiply the y to bring it to the other side. And I'll clean this up first so you see what we've got here. 1/2. We could factor it out because it's in both parts here. And this is where we're multiplying to bring y to this side. So our y term is square root of x to the x power. And now we want to evaluate at 1. So the square root of 1 is 1. To the first power is 1. And putting 1 in here, the natural log of 1 is 0. So 1/2 times 0. So we'll have 1 times 1/2. So I think 1/2, letter C, would be my choice for question 10. And in 11, find the value when it reverses direction. Well, remember, it can only reverse direction where velocity is 0. So we want to find s prime of t, which is our velocity function, 2t minus 3. So v of t is equal to 0 only at t equals 3/2. So that's the only time when it could reverse direction. So when time is less than 3/2, our velocity would be less than 0, so it'd be moving to the left. And when t is greater than 3/2, our velocity would be positive, and it would be moving to the right. So it can only change directions at 3/2. And another position function, find the value of t at which acceleration is 0. Well, velocity would be the first derivative, 3t squared minus 2t. Acceleration is the second derivative, 6t minus 2. So when is acceleration equal to 0? That would be at 1/3. And linearization is another, it's a synonym for a linear approximation. So the square root of 16.2. So f of x is our square root function, and f prime, 1/2 square root of x, our point of tangency close by would be the square root of 16, would give us a perfect point of tangency at 16,4. So we want f prime at that point of tangency. So 1/2 square root of 16 would give us a slope of 1/8. So our tangent line, y minus 4 equals 1/8, x minus 16. And now we want to evaluate it when x is 16.2. So 16.2 would leave us a 2/10 in here. 2/10 or 1/5, whichever you prefer. And then we would add the 4 to the other side. So 4 and 1/40 would be our approximation. In 14, so the differential dy, remember that if we find dy dx, then each part individually is a differential, so we would want to keep the dy and move the dx to the other side. So let's not worry about that here until we find our derivative. So dy dx is equal to 2x, and if I move the 2x to this side, so our differential for dy has the value of 2x dx, and delta x becomes our dx. So when x is equal to 2, and dx, or delta x, is equal to 1, our differential will be 4. So that's a problem. We really haven't seen the terminology, but there's really not much to it. Another linear approximation. So what do we know? Well, think about this graph. E to the 0 power is 1. So our easy point of tangency is when x is equal to 0, we'll get 1 for y. Our derivative, the derivative of e to a glob is e to a glob. The chain rule on the glob puts a -3 here. So we would want to do our f prime at 0. So that would come up with -3 times 1, or -3 for our slope. So our tangent line, y minus 1 equals -3, x minus 0. And then we want to let, and again, I don't need to substitute. I'm forgetting what our question is here. We just want the linear approximation, so we're not plugging in any specific value of x. So let's just clean this up as a formula. So -3x plus 1. So that looks like choice C. So this would be the formula, and then you could let x be equal to whatever value you wanted to, as long as you stayed close to the value of 0. So as long as you stayed in the same neighborhood. All right, a second derivative. Let's do implicit differentiation. Don't forget the chain rule on the y term. So we can solve for y prime, subtract the 3x to the other side, divide by 3y squared. So there's our first derivative. And our second derivative, we'll do our quotient rule. So we'll have low d high minus high d low. Don't forget the chain rule. So this y prime we want to replace. So that y prime we can replace with the value that we just found. So we're going to replace that y prime, and my video is getting long, so I'm going to actually cheat and replace it right away. So negative x squared over y squared when we replace y prime here. So we can do some canceling. So this y will cancel with one of those. And then we don't want a complex fraction. So to save some writing, I can multiply by y over y. Let's see if we can clean this up. So now we have 2xy cubed. Don't forget to distribute. And here the y's cancel. That was my purpose. Negative times negative will be positive. 2x to the fourth. And our denominator is y to the fifth. And if we factor the GCF, so if we factor out with the negative sign, let's factor a 2 and an x. So we would have a y cubed plus an x cubed. Remember, we're looking for one more substitution. So this should look familiar. Y cubed plus x cubed. Right there it is in our original. So that value gets replaced with 1. So our expression simplified nicely to the opposite of 2x over y to the fifth. And there it is. All right. And another straight line motion problem. So we want the total distance traveled in 3 seconds. Well, let's find the velocity. So we'll have 6t minus 18t plus 12. When is the velocity equal to 0? So these all start looking alike here. I'm factoring, sorry, not a 0. I'm factoring a 6. So a t minus 1 and a t minus 2. So the velocity is equal to 0. Our critical numbers, when it is stopped, would be at 1 second and at 2 seconds. If we choose a number smaller than both of those, the object would have positive velocity because both parentheses would be positive. So to start out with, on our interval from 0 up until 1, we know it's going to be moving to the right. And then when we choose a number between 1 and 2, we'll see that the first parenthesis will be positive, but the second will still be negative. So then our object will be moving to the left between these 2 times. And then when it hits 2 seconds, and when it's larger than 2 seconds, both parentheses will be positive, so then it will be moving to the right again. So all we need to do is find out then how far is it at the end of our desired interval. So we're going to find these values by plugging into the position function, not the velocity. So I'll pause the video and do that arithmetic. All right, so I believe at 0, we can all see that one without a calculator. We're at 0 meters. And when we put 1 in, we would be at 5 meters. So now we've covered a distance of 5. And when we put 2 in for the time, we will be at 4 meters. So it's traveled another 1 meter between those two. And at 3, we will be at 9 meters. So we've traveled another 5 meters. So our total distance traveled is 11 meters for our total distance over the interval from 0 to 3 seconds. And that should do it.